Hello class, today we are going to be starting a new unit, Unit 6, and we're going to start off with Lesson 1. This is 6.1 Radian measure. So we've talked about it a lot, you've probably heard. We no longer work with degrees when we do trigonometry now and angle measures. We're now going to use something called radians. Okay, so eventually I do want you playing around on your calculator to make sure that you can find the radian button, and you should be able to go between radians and degrees and be able to know how to do that. Okay, so let's start off with just reviewing some things we know from trigonometry. Okay, so we remember that an angle in standard position is one where the vertex of the angle is at the origin. Okay, and the initial arm lies on the x-axis. Okay, so for example, this angle here in blue is in standard position, okay, because its initial arm here lies on the positive x-axis. Okay, so always coming out here. And in blue, we would call that theta. Okay, and in red here, we call that beta. Okay, they are just theta and beta are just what we use to represent unknown angles. All right, so just a reminder, a positive angle is always formed by a counterclockwise rotation. Okay, so coming up from the positive x-axis and then going counterclockwise. Okay, a negative angle is formed by a clockwise rotation of the terminal arm. So you're still starting here, but you're going this way clockwise. Okay, so this angle measure here would be negative, and then if you wanted to find its positive version, it would be what I've indicated in the dotted angle measure. Okay. And just a reminder, with our quadrants, we always label this quadrant 1, 2, 3, and 4, starting at the top right and then moving around. All right, definition for what a principal angle is. So a principal angle, it is the counterclockwise angle between the initial arm and the terminal arm. Okay, so that's what I've highlighted here in drawn in blue. Okay, we often denote the principal angle by using theta. Okay, so theta is always an angle between 0 and 360 degrees, so it's always our positive angle. The related acute angle, sometimes referred to as the reference angle, is the angle between the terminal arm and the x-axis. And notice how here I've added in, it's the nearest x-axis. So that's why in this case here, this angle's blue arm creates a related acute angle that's equivalent to its actual principal angle here. However, if I were to draw the angle, okay, for example, what we have drawn here, if this was the angle, then the related acute angle would be the little part I've indicated here in red, because that's the angle made with the terminal arm and the nearest x-axis. So because it's always to the nearest x-axis, we always say that this angle is positive. It's kind of like me saying, what is the shortest angular distance to the nearest x-axis? Okay, and we know that means that it's between 0 and 90 degrees. And we often denote the related acute angle with beta. So we're used to using the degree measure used for trig applications. We know that one complete revolution around the circle is always 360. So we come up here, we know 0, 90, 180, 270, 360. But today, obviously, we're going to rename those using a different unit of measure. So you may see it in math and also in science. A more useful unit of measure is a unit called the radian. Okay. So what is a radian? It is one radius's worth of distance on the edge of the circle. So I know that kind of sounds confusing, but I want you to kind of think of it as an angle measure that relates how far it travels on the outside of the circle in relation to the actual radius of the circle it's creating. Okay. Before we go into the definition, keep in mind that in a circle, the angle formed at the center of the circle by two radii is called the central angle. Okay, so I'm going to show that here in a diagram. So here's our circle, okay? We start off at one point here, okay? And notice that by drawing two radius lines, so in blue, we've created an angle inside, okay? So this is what we call the central angle, okay? What's along the side here, so this angle is created by two radiuses of obviously the same length, but what we care about is this length that covers along the circumference of the circle. So we call that the arc length. So if you want to highlight that here. So A here is our arc length, and then we have our central angle inside here. So this angle is found in radians by relating this red part, the arc length, to the length of the radius. Okay. So the general formula is, okay, you can highlight this here, that theta, so theta, this is going to be in radians. So let me just write that. Okay, so our answer here is going to be in radians. Okay, so the answer you get when you divide the arc length by the radius is just going to be in radians. You're not going to say degrees. Okay, so highlight this formula. Now keep in mind, I want you to think of the unit measures here. So if I were to sub in a number for arc length, I know that that would have to be in a unit measure, say centimeters. When I sub in a unit measure for radius, that would also be in a unit measure like centimeters. So if I do a unit divided by a unit that are the same, that means the centimeters actually cancel out, and I'm left with no unit of measure after. Okay, so what I mean is that I'm just left with something like theta equals 2. Okay, so for example, you could be left with theta equals 1.1. Okay, and I'm not going to put anything here because I already know that this is in radians. Okay, so oftentimes the angle is a real number without any units. You're going to see later on, sometimes in math, we do write rad after it, just as a little reminder, but other than that, a lot of times there won't be, like with degrees, we put that little degree symbol. With radians, there is not a symbol that we put. Okay. All right, so let's practice an example for that. It says, what is the radian measure of theta given a radius of 4 and an arc length of 10 centimeters? Okay, so remember, this all has to do with the angle around the circle. So I want you to visualize what I'm asking here. So draw a circle, okay? Draw two radius lengths of 4. Okay. We know the angle inside is the central angle, and we want to find the measure of this angle if we know the radius is 4, and if we know we have traveled along the circle's edge 10 centimeters. So that means they gave us the arc length of 10 and the R value of 4. So we're going to find out what that angle measures in radians. So we're going to do theta equals A over R. So that's going to be 10 divided by 4. Okay, and that gives us 2.5. So like I said, you can just say theta equals 2.5 and leave it because that implies radians. If it makes you feel more comfortable, you can actually put the word rads or radians right after. Okay, so 2.5 radians. All right, so this part is all good. We figured out how to find something in radians, but what we need to go over right now is what a radian is. So we know that angle is 2.5 radians, but we have no idea what that measure is or an idea of what that is. So that's what we're going to do on the next page. All right, so we should be asking ourselves, how many degrees is 1 radian, right? How do they kind of relate to each other? So let's keep in mind that a radian is the size of the angle that is subtended at the center by an arc with a length that is equal to the radius. Okay, so I know this is a lot of confusing words at first, so try to take it step by step. Let's highlight here. So it's the size of an angle created by an arc with a length that is equal to its radius. So on the previous example, on the previous page, obviously the arc length and the radius were not equal. Okay. Now I'm telling you that 1 radian is when the radius here, and then the arc length is the same as the radius. So that means all 3 of these are the same length, is essentially what it's saying. That is the definition of 1 radian. Highlight that here. Okay, so let's figure out with our formula what that means, right? So we know theta equals A over R, and based on this case, they're telling us that the arc length is the same as the radius. So A equals R. So I'm going to write that as R divided by R, and that leaves us with the number 1, right? So 1 radian is when A is equal to R. All right, how is that going to help us with degrees? So I want you to start thinking, before we go over the formal number, I want you to try to do some guessing of what you think 1 radian is, just based on our shape here. So looking at this pi, right, this kind of pi shape here, I would say if they have all 3 sides the same, right, it looks close to an equilateral triangle. It's not exact because obviously this curved edge here is not a straight line connecting the two. Okay, so we know it's not exact, but that's why I said it looks close to an equilateral triangle. Okay, so let's do that in purple. Okay, so this guy here looks like our equilateral triangle. Okay. What do we know about equilateral triangles? We know that, here. Okay. Equilateral triangles, we know they all have all 3 angles inside are 60 degrees each, right? So I'm going to guess that the angles inside here are roughly 60 degrees each. So my conclusion is going to be that this one angle measure inside here, right, is going to be close to 60. Okay. So just speculation, we're going to assume that 1 radian, and then notice I say is approximately equal to 60 degrees. Okay, that's kind of like our educated guess. Obviously, it's not going to be exactly that because it's not a perfect triangle. So let's go ahead now and find the exact value. Okay, so let's consider the arc length created by an angle of 360. So now we're taking that radius, we're rotating it all the way around and overlapping itself. Okay, so that means we've traveled the whole circle. So if I do theta equals A over R, if I have traveled around the whole outside of the circle, that's the same thing as saying that you have traveled the entire circumference. Okay, so that's why here we know the definition of circumference is 2 pi r. So essentially, when I ask you for the arc length of a 360-degree rotation, the arc length is 2 pi r. And then we're going to do 2 pi r as our A, divided by the radius r. And what happens there is that the r's cancel out, and I'm left with 2 pi radians. Okay. So this full rotation is equivalent to 2 pi radians. So that means we just discovered that the relationship between the two right now is that 360 degrees is equal to 2 pi radians. All right, now this is good. We found kind of a relationship between these two, but I still haven't figured out how many degrees is 1 radian. So let's keep breaking it down. Let's divide by 2 on both sides and see what other conclusion we can get. When we divide by 2, what happens next is I get that pi radians is equal to 180 degrees. All right, so a few things I found out. So 180 degrees is pi, a full rotation is 2 pi. Okay. All right, now we really just want to get what 1 radian is, not what pi radians is. All right, so we know 180 degrees equals pi radians. I want to get rid of this pi and be left with 1. So I'm going to divide out pi from both sides. When I divide both sides by pi, I get left with the statement that 1 radian is approximately equal to 57.3 degrees. Okay, so if you enter that into your calculator, so 1 radian is approximately 57.3 degrees. Right? So remember, that represents when the angle created has an arc length that's equal to the radius. Right? And look here, we had guessed it was close to 60 and we were very close, right? 57.3 degrees. So let's highlight that. Okay, so 1 radian is 57.3. Okay. So if you want, you can kind of go back to that first page here and we can add in some things that we've just learned. So we know that 360 here, right, the full rotation is 2 pi. And we also learned from that example that 180 is considered pi, okay, in radians. Okay. All right. So before we go on to other questions, I'm just going to get you guys used to filling in what the radian values are for special angles. So what we're going to do is we're going to divide up this whole circle into our special angles, right? We're used to doing that. We're used to 30, 60, 90, and 45 degrees. Keep in mind, this is going to get a little chaotic looking. It's nothing we can't handle, but what I mean by that is, as you can see, there's going to be a lot of things we're writing in. So I want everyone right now to get out a bunch of different colors, okay? You need a minimum of 4 different colors that I've kind of shown here, okay? So get out those colors now, okay? And basically what we're doing today is just counting and reducing fractions based on what we know. All right, so we're going to start. Here we have 0, okay, so 0 degrees and 0 radians. We're going to first go up by intervals of 90 degrees. So because 180 degrees, so kind of at the side, or I'm just going to say at the side here, because 180 degrees was equal to pi radians, if I wanted to represent 90 degrees, I would divide this by 2 and divide this by 2, which would lead to the conclusion that 90 degrees was equal to pi over 2 radians. So whenever you're going by intervals of 90, it's always intervals of pi over 2. All right, so let's start counting. Okay, and I'm going to use some colors here. Okay, so our purple. All right, so like I said, I'm going to highlight here in purple. So our first one is 0 degrees. Okay, we're going to start there. Our next interval will be 90 degrees. Okay, that's here. We are going to refer to that as pi over 2. All right, our next interval of 90 degrees brings us to 180. So how many pi over 2's is that? This is 2 pi over 2, okay? And 2 pi over 2 reduces to pi. Okay, so you can also write that as 2 pi over 2. Notice that we're just counting. So pi over 2 remains, and then you just increase the number. So that's 1 pi over 2, 2 pi over 2, which means that coming down here is 3 rotations of pi over 2. Okay, so we're going to write that as 3 pi over 2. So now we've discovered 90 is pi over 2, 270 is 3 pi over 2. And then when we come right back up, that means that's 1, 2, 3, 4 rotations of pi over 2. So that's why we get 4 pi over 2, and obviously we know that reduces to 2 pi. Okay, so we're always putting our fractions in lowest terms. All right, so same kind of pattern. We're going to move on now to intervals of 60 degrees. So if you think about it, there are 3 60-degree angles that cut up half a circle. Okay, so that means if half a circle is pi, that means we have to do pi divided by 3 to get 60. And you're going to get used to using all these terms, but pi over 3 radians represents 60 degrees. So we're going to do counting with that. So our first 60-degree angle appears here. Okay, so have your different color. All right, so that is pi over 3. Right, 1 pi over 3. Our second 60-degree angle, okay, so that means we're going to go 30 and then 30. So our second 60-degree angle is right here. That is 1, 2, so that's 2 rotations of pi over 3. So that's why I've labeled that 2 pi over 3 here. I'll fix that there. 2 pi over 3. There we go. All right, now we have to do our next rotation. So that's 60, that's 120. Now we're doing another 60, and that's going to bring us to an overlap at the 180 mark. Okay, so that's 1, 2. This will be 3 rotations of pi over 3. Okay, so that's 3 pi over 3, which reduces to pi. So you should be noticing the pattern. All right, now we're going to do 4 pi over 3. So the fourth 60-degree angle. Okay, so we write that as 4 pi over 3. All right, and then we're going to do the fifth 60-degree angle. Oops, sorry, I'll fix that. And that is the fifth 60-degree interval. So that means we are at 5 sets of pi over 3. And then we're going to finish it off by coming full circle. Okay, so we're going to overlap here, and that is 6 rotations of pi over 3. 6 pi over 3 reduces to 2 pi. Okay, so hopefully you're getting the hang of it. Like I said, you just are doing counting and reducing. All right, so let's work with green now. All right, so green is going to represent intervals of 30 degrees. So 30 degrees is represented by pi over 6. And that's because, remember, pi represents 180. So if you divide 180 degrees by 6, that gives you 30 degrees. So that's why 30 degrees is pi over 6 radians. I know it's confusing because you wish the pi over 6 matched with the 60 and you wish pi over 3 matched with the 30. That's not the case. Always remember it's the swap. All right, so let's begin. Let's start with the first 30 degrees, which is right here. Okay, so right there, this guy is just pi over 6. All right, the next one is going to overlap with the 60 mark, right? Right, so that is the second set of pi over 6. Right. So that is 2 pi over 6, and obviously we would reduce that to pi over 3. All right, our next set will be at the 90 mark. So that's 1, 2, 3, that's 3 sets of 30. So that's 3 pi over 6. Next one is again going to overlap here. So that's 1, 2, 3, that's 4 sets of 30. So that's 4 pi over 6. And we know that reduces to 2 pi over 3. That's why they're equivalent. All right, our next one is here. 1, 2, 3, 4, 5. That's 5 intervals of 30, so that is 5 pi over 6. Okay, and then we're going to overlap here at the pi mark, and that will be the 6th set of 30. So that's 6 pi over 6, which gives us pi when reduced. All right, our next one here, if that was 6 pi over 6, that means this guy is 7 pi over 6. All right, our next one is going to be an overlap here. Sorry, let me fix that one. All right, that's 7 pi over 6. This one's going to be, this next green one then is going to be 8 pi over 6. And 8 pi over 6 reduces to 4 pi over 3, which we already had. All right, and then our next one is going to be at the 270 mark. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, and this one should be 9 pi over 6. 9 pi over 6 reduces to 3 pi over 2. All right, our next one will be here. Sorry. Okay, it's going to overlap, and that one should be our 10th interval, so our 10th pi over 6, which reduces to 5 pi over 3. All right, and then our second last one is here, and that should be 11 rotations, or sorry, 11 sets of 30, so we get 11 pi over 6. And then obviously we overlap when we come back for a full rotation, and that means that we do 12 sets of 30, and that leads to 12 pi over 6. 12 pi over 6 reduces to 2 pi. All right, we are almost there. Our last sets to do are sets of 45 degrees. We're going to do that in blue. All right, 45 degrees. So we know that there are 4 sets of 45 degrees in half a rotation. All right. So that's why 45 degrees is pi divided by 4 radians. Okay. So let's highlight our first one. That is 1 pi over 4. All right, our next one is going to be at the 90 mark. Right? That is our second set of pi over 4. So we're going to write that as 2 pi over 4, right? And that reduces pi over 2. Our next 45 degree angle will be here, so that will be the third set of itself. So that's 3 sets of pi over 4. All right, our next one is going to overlap at the pi mark. Okay, so that's going to be 1, 2, 3. This one should be 4 pi over 4, reduces to pi. All right, next one is in the center here. If that's 4 pi over 4, then the next one is 5 pi over 4. Then we're going to hit it again at the 270 mark. If that was 5 pi over 4, this one is going to be 6 pi over 4, and that makes sense. It reduces to 3 pi over 2. Then we have our next one, 7 pi over 4. Move that there. And then our full rotation is when we come all the way back around. Okay. And that leaves us with 8 pi over 4, so 8 sets of 45. and 8 pi over 4 reduces to 2 pi. Okay, so I know hopefully going over it this way made it better than looking at it when it's all done. But basically, always refer to this for easy ways of counting. Okay. All right, let's move on to the next page. So now we need to determine what is the relationship between degrees and radians. Okay, or how can we convert between the two? So if we want to go from degrees to radians, we have to think of this. So we know 360 degrees is equal to 2 pi radians. Okay. So now I want to figure out what 1 degree is. Okay, so if I want to get what 1 degree is in radians, that means I have to divide 360 by itself to get 1, right? And whatever I do to one side, I do to the other. So in your calculator, I want you to type in what is 2 pi divided by 360. You will get another number, okay? Or you can just reduce it to pi over 180 radians, okay? And this is usually what we work with. But if you wanted to write it, so radians can be written in its pi form like this, or it can be written in decimal form, okay? So it doesn't matter which one. Usually when I have you convert, I'm going to have you keep it in lowest terms pi form. All right, what if we're going the opposite direction? What if I want to know what radians is in degrees? What conversion method do we have to use? Okay, and we kind of went over something similar to this already. So start off with the same equation, 360 equals 2 pi rads. We want to get 1 rad on its own, so we're going to divide both sides by 2 pi. Right? And when we do that, we get 180 divided by pi. And remember, this is how we got that, that other degree before, right? About 57.3. That's what this is equivalent to. Okay, but we're just writing it in its pi form. Okay, so it's just 2 different ways of writing it. All right, so if I ask you to convert from degree measure to radian measure, so if you're going from degrees to radians, that means you have to multiply your degree measure by pi over 180. All right, so we're getting that from here. And then vice versa, if you're going from radians to degrees, then you have to multiply by 180 over pi. Okay, that's what we got from right here. All right, so let's practice this. It says convert each angle to degrees, convert each angle in degrees to the exact radian measure. So when I say exact, that means I mean no decimals. So that's a hint that you're going to write it in lowest terms, okay? So 20 times pi over 180, right? That's 20 pi over 180, and then put it in lowest terms, pi over 9. 30 degrees times pi over 180, so that's 30 pi over 180, reduced to lowest terms, pi over 6. And hopefully you're recognizing that from the previous page. 225 times pi over 180, when reduced to lowest terms, is 5 pi over 4. Again, I want you to get used to recognizing this. So 5 pi over 4 is another way of saying 5 sets of pi over 4. And in my head, I'm remembering from before, that means 5 sets of 45 degrees. And that makes sense. 225 is 5 sets of 45. 285. This one, when reduced, 285 pi over 180 gives us 19 pi over 12. Okay, so not all of them look very nice, but this is how we convert to radian measure. Like I said, if they didn't say exact, you could actually do 19 times the pi button divided by 12 and get a number 2. All right, so whenever an angle, remember, whenever an angle is expressed without a unit, so without a unit beside it, so just a number like 2, it is understood to be in radians. Okay, we often write radians after the number as a reminder that it's an angle. Okay, so basically what I said before on the previous page. All right, we are going to convert each radian measure to degree measure and then sketch it about a circle of radius 1. So these are in radians. We can already tell with the pi form. So we're multiplying by 180 over pi. So you should start canceling things out right away. So for example, I know 180 divided by 4 is 45. So that's why I canceled out here 45. Okay. The pi's here are going to cancel out. So I'm going to be left with 3 times 45. And that's 135 degrees. Just for practice and drawing, if we start right here, right, then I want you to just, it doesn't have to be perfect, but try to visualize 3 sets of 45. So if I'm starting at the blue, I went 1 set of 45, 2 sets of 45 is 90, third set would be about right here. So this is the arc length, and then the blue, okay, so this blue angle here is 3 pi over 4. All right, 11 pi over 6 times 180 over pi. Again, pi's cancel out. I can reduce 180 over 6 as 30 over 1. So I'm left with 11 times 30, okay, and that's 330 degrees. So again, I want you to draw your circle, and I want you to visualize drawing 11 30-degree intervals. Okay, so I know that one's hard because they're so small. So here, if I am starting at the blue line, I do 1, 2, 3, that's at 90, 4, 5, 6, that's at 180, 7, 8, 9, 10, and then 11. So it's the last 30 before I do a full rotation. So that angle there is 11 pi over 6. All right, here's an example of where radians, they put radians here to help remind you that 1.75 is an angle. I could have not given you the radians at all and just said 1.75, and you would have to know that it meant radians. Okay, so this one's just different. It's not in its pi form. So 1.75 times 180 over pi will give us 315 over pi. And that is approximately equal to 100.3 degrees rounded. So for that one here, it might just be easier for us to draw visually. As you can see, I've kind of gone a little bit past the 90-degree mark. All right, the next example says a point is rotated about a circle of radius 1. Its start and finish are shown. State the rotation in radian measure and in degree measure. Okay, so here we can see that we're starting from here and rotating in the clockwise direction. So right away I know this is a negative angle. So in degree measure we know this is negative 180 degrees. Okay, and notice theta should always be positive, so I'm just going to put the little negative symbol up here to show that I know I'm dealing with the negative version of theta. Okay, so it's negative, so what here in red is negative 180. So now we're going to state that in radian measure. Okay, so that means we take the negative 180 and we multiply it by pi over 180. The 180s are going to cancel out, and we are going to be left with negative pi radians. If I had asked you for the positive version of this angle, that would mean that you would be going from here in the counterclockwise direction, and the positive version of this would be positive 180 and obviously just pi radians. All right, so this one here we can label normally as theta because it is counterclockwise. So the degree measure here, sorry, I can't see where it is. There it is. Okay, so we know here this rotation is 270 degrees. All right, so 270 times pi over 180, that gets reduced to 3 pi over 2. All right, so this was 270, and its radian measure 3 pi over 2. So you can also think of 270 as 3 rotations of 90-degree intervals, because pi over 2 is always 90. All right, so we're done with that part with radians. Now we're going to kind of move on to some word problems. Radians will still be involved there. Okay, but this part is where students kind of get the most confused, okay? So there's just a lot of formulas, nothing we can't handle, but we'll go through each example. And all these examples are very similar to ones in the textbook. All right, so notice the formulas I have on this page here are not formulas that you can find in the textbook, okay? They kind of just want you to work with common sense to come up with these formulas. So always feel free to refer to these notes for this if you find it helpful. Okay, so angular velocity. Okay, so just short form AV. So that is asking, okay, what is the ratio between the angle covered in one revolution divided by the time it takes to complete one revolution? So basically, instead of me asking you how far are you traveling in a certain amount of time, like distance-wise, angular velocity means I'm saying how quickly am I turning through an angle over a certain amount of time. So basically, in 1 second, how many angle degrees did I travel? Okay, so that's what we mean by angle velocity. Notice that the angle covered in one revolution is one full turn of a circle, so that means it's always 2 pi, right? We've learned that 360 degrees is always 2 pi, so it's 2 pi divided by the time it takes to complete one revolution. The distance covered in x time. So the distance something covers in x time is always going to be the distance around the circle, which is the circumference, and then you multiply that by how many times that rotates. Okay, so if there's 10 centimeters in the circumference, then when I rotate once, I've traveled 10 centimeters. If I rotate twice, I've traveled 20. 3 rotations, I've traveled 30. So that's essentially the concept here. So you need to know what the circumference is, and then you multiply by the number of revolutions completed in that time. And that will be how far it's traveled. Okay, because it may not travel full revolutions, it may travel 0.3 of a revolution. All right, if I ask you about the number of revolutions in a certain amount of time. Okay, so this one, okay, you can ignore the purple here, that's for the next question. So the number of revolutions traveled in a given amount of time is going to be the angular distance covered in that amount of time. So angular distance is, I mean, what is the angle measure that you traveled? So did you travel 30 degrees in 5 seconds? So you would put 30 degrees, but obviously you'd put it in radian measure. Okay, we're working with radians now. Divided by the angular distance covered in one revolution. So we already know the answer to that. We know the angle covered in one revolution is 2 pi. Okay. So you're going to take the time, or the angle covered in a certain amount of time, divided by 2 pi. Okay, and that will tell you how many revolutions occurred. So we're going to use these 3 examples and the next 2 examples here. Yeah. All right, it says the London Eye Ferris wheel has a diameter of 135 meters and completes 1 revolution in 30 minutes. Determine the angular velocity in radians per second. All right, so angular velocity. So basically they're saying, what angle measure does the wheel travel through in 1 second? Okay. All right, so I want you to think of this here. Okay. So we know it's going to be 2 pi, okay, divided by the time of 1 revolution, right? So I'm looking up here in yellow. 2 pi divided by the time for 1 revolution. Because they want it in seconds, and because unfortunately our question gave us how long 1 revolution is in minutes, we just have to convert. Okay, so we're just converting 30 minutes to seconds. So we're doing 30 times 60. So that means 1 revolution is completed in 1800 seconds. So we're going to go put that in our formula. So 2 pi radians divided by 1800 seconds. So that's saying you do 1 revolution in 1800 seconds. Okay? And that's approximately equal to 0.0035 rads per second. Okay? So that's the angle measure it travels in 1 second. Part B. How far has the rider traveled at 10 minutes into the ride? So when they're saying how far has he traveled, they basically want to know the distance traveled. So I want you to think of the arc length. Okay, so distance traveled here is the length around the circle. Okay, so that's distance around the circle, so circumference, or what part of the circumference has been traveled, basically. All right, so we're going to use our formula here in green. So distance in x time. So distance traveled in 10 minutes should be equal to the circumference times the number of revolutions that were done in 10 minutes. Okay. So we will be able to find the circumference because we know circumference is always 2 pi r. Okay. So we know the radius because they gave us the diameter. So we just take the diameter and divide it by 2, and that will be our radius. What we don't know is the number of revolutions done in 10 minutes. So we're going to have to do some ratios at the side here to figure that out. Okay. What do we know? Okay. So they always give you enough information that you'll be able to solve for the missing value. What we do know from the question is that it completes 1 revolution. Okay, so I'll highlight this in kind of purple here. So we know it completes 1 revolution in 30 minutes. Okay? But we want to know the number of revolutions in 10 minutes. So we can set up a proportion. So 1 rev over 30 minutes is equivalent to how many revolutions in 10 minutes. So what we're solving for is x. Okay, so this is x here. Okay. All right, to solve this, you cross multiply. So you get 10 equals 30x. You divide by 30 and you get x equals 1 over 3. So that means in 10 minutes, it only covers 1/3 of a revolution. So it's obviously moving slowly. Okay, so it hasn't even completed a full revolution yet. Okay. So we're going to go back to our line. Circumference is 2 pi times 67.5, our radius. Okay. And then number of revs in 10 minutes is 1/3. So that leaves us with approximately 141.4 meters traveled. Okay, so the rider has traveled 141.4 meters in 10 minutes. Okay, our next question. It says a wheel is rotating at an angular velocity of 0.10 pi radians per second. So right away, when you see something in radians per second, that's obviously discussing an angle measure per second. Well, a point on the circumference of the wheel travels 8.4 pi meters in 30 seconds. Okay, so because this one's in meters, okay, that means they're talking about the distance on the outside of the circle. Because this one's in radians, it's referring to angles. Okay, so I want you to be careful with that because students get confused that just because pi is here, they think that means it's an angle. Okay, but you have to look at the context. All they're saying is 8.4 times and then the value of pi, and they're saying that whole number is meters. Okay, so just be careful with that. All right, so it says how many revolutions does the wheel make in 1 minute? So that's going to come up here, and we're going to do this formula. Okay, so we have to find the angle measure traveled in 1 minute and divide it by 2 pi. Okay. All right, so the angular distance covered in 1 minute. So what our problem is here is that here in yellow, the top line, we know the angle measure covered in 1 second, but we don't know what it is in 1 minute. So we can set up a proportion to solve that. Okay. So we're going to say we know it travels 0.10 pi rads in 1 second, and that should be equivalent to, and then our x is our unknown, divided by and we want to know what it is in 60 seconds because that's 1 minute. Okay, so we're solving for x here. All right, so you should get 60 times 0.10 pi, and that gives us 6 pi. Okay, so you can just leave it in the 6 pi form. All right, so the angular distance covered in 1 minute is 6 pi. Okay. So we do 6 pi divided by 2 pi, and that leaves us with an even number, a nice whole number of 3 revolutions. So we say the wheel made 3 revolutions in 1 minute. Okay, so it turned 3 times in 1 minute here. All right, and lastly, it's saying what is the radius of the wheel? So this one's new. You're not going to find that formula up here, but it is hidden within it. So I want you to look at all the formulas and discover which formula involves radius at some point in the formula. And that you should come to the distance traveled in x time formula. This is the only one that has radius in it because you have to deal with circumference. So we are going to use this formula and then rearrange and isolate for r. Okay, so let's come down here. So we know we have to deal with the distance traveled in a certain amount of time. So right away you should be thinking in the question, did they give us anything to do with distance traveled in a certain amount of time? And they did. They told us here 8.4 pi meters in 30 seconds. So we're going to work with that. Okay. So we're going to set up the distance traveled in 30 seconds is equal to circumference times the number of revolutions in 30 seconds. Okay. All right, we already know, okay, that it travels 8.4 pi meters in 30 seconds. So they gave us this. Okay, so I filled in this side. Our circumference is unknown. We know it's 2 pi r, and we're solving for r. So now I'm going to show you how we get the number of revolutions in 30 seconds. All right, so we're going to go to the side here, and again, deal with what you know. From the previous part of the question, we knew that it travels 3 revolutions in 60 seconds. All right, from this question here, right? 3 revs in 1 minute, so we can write that as 3 revs in 60 seconds. Okay, so I'm going to draw the arrow here. But we want to know the number of revolutions in 30 seconds. Okay, so you can do that in your head if you want, or set up your ratio like I did here. So we are solving for x. That's what we care about here. So we're going to do x divided by 30. Okay, when we cross multiply, we're going to get 60x equals 90. Divide both sides by 60 to get x on its own, and we get 1.5 revolutions. So it travels 1.5 revolutions in 60 seconds, and you're going to plug that into your formula. All right, and now we can solve for r. So on the next line, I kept 8.4 pi, and then I just did 2 times 1.5. 2 times 1.5 gave me 3 pi r. I want r on its own, so I'm going to divide both sides by 3 pi. What happens here is that the pi's cancel out, right? And then I'm left with 8.4 divided by 3, which is 2.8 meters. So our final answer is that the radius is 2.8 meters. Okay, as you can see, it's a lot of information that was packed in for just one lesson in one section of the textbook. So if you want, you can take your time, maybe do half of the homework today, half the next day, but I have given you 2 days to kind of absorb all of this information, okay, before we move on to 6.2. Let me know if you have any questions. It's okay to feel a little overwhelmed after seeing all this. Just do one example at a time, and eventually you will get the hang of it, okay? Looking forward to teaching you for 6.2.